Good morning, class. I hope everybody's staying healthy, staying safe, following the rules, and hopefully things will get back to normal pretty soon. So yeah, just do your social distancing and stay clean. So today we're going to get into chapter 29, which is about refrigerant charging. So this is for mile 135. So let's go ahead and jump into chapter 29, refrigerant system charging. So the objectives are explain how to determine the correct amount of charge for a split system, discuss the difference between liquid charging and vapor charging, explain how to charge systems that use zeotropic refrigerants, determine the correct superheat for a fixed restriction air conditioning system using the superheat charging chart, determine the correct subcooling for a thermostatic expansion valve air conditioning system using a charging chart, list the variables that affect the system operating pressures, and define the AHRI standard equipment rating condition. So, introduction, outside influences, balancing act, undercharging, overcharging. Let's get into that. So, low evaporator airflow due to dirt, improper fan speed, or poor duct design can mimic the pressure readings of an undercharged system. Dirt, right there, they're talking about well, most likely they're talking about dirty filters. We went over that in class before. A really dirty filter is going to cause really poor airflow across that evap coil, and it's gonna mimic an undercharged system because the temperature is going to drop. The only thing keeping that coil from freezing is the warm return air going across it. You got a dirty filter or a dirty coil and you're not getting that warm air going across there, you don't have that heat transfer from the coil to the ambient air, that coil is just going to ice up. All the condensation that forms on that coil will freeze, and next thing you know, you got a block of ice. Subcool is going to drop, and it's going to appear that your system is severely undercharged when it's really just iced up because of a dirty coil, which is causing poor airflow. Airflow is one of the three, uh, airflow is two of the three mass fluid flows. So definitely check filters on service calls. So the level of refrigerant charge is a delicate balancing act. Too little refrigerant or too much refrigerant can reduce the system's performance. Undercharging can reduce oil return back to the compressor, cause high compression ratios, and lead to compressor overheating. Overcharging can cause liquid to flood back to the compressor, leading to compressor failure. Compressors are vapor pumps, not liquid pumps. So you get liquid flood back to your compressor, you're gonna break it. It will also cause liquid refrigerant to back up in the condenser, increasing the operating head pressure and reducing the system efficiency. Leak testing. Check before charging. Always check for leaks if a system needs to be charged. Always check for leaks before evacuating and charging a system. So, we've gone over that many times in class, so I think everybody's pretty familiar with that concept. After you make a repair on a system, after you open a system for any reason, when you put it back together, first, like I said, whenever you open a system, you got to put in a new filter dryer. But assuming we put the new filter dryer already, put the system back together, we brace everything in, first thing you're going to do is leak check. Pressurize that thing with nitrogen, pull out your soap bubble, make sure you don't have leaks anywhere before you waste time trying to pull an evacuation that'll never actually come down within range because it's a leaky system. So definitely always want to leak check first and before charging the system. Well, before evacuating, and then evacuate definitely before charging. Leak testing, always find the leak. Adding refrigerant without finding and repairing a leak costs the customer money. The system will operate inefficiently by using more energy to produce less cooling. So we've gone over it many times, but runtime is one of the biggest factors in energy efficiency. If a system is not performing, it's just running, but it's not quite performing, it will cool, but it'll take way more time to cool at, 75% capacity than it will at 100% capacity. So that's a huge waste of energy. And then also they're wasting money by literally dumping the refrigerant they just paid for into the air. Some customers will ask you to do that. They'll be like, can you just top me off so I can just get through the summer? And within reason, I mean, I guess you can. Some people do. It just all depends. If it's really low, I'm gonna recommend a leak check and a repair. But I mean, if it's just off by a little bit, maybe. But it's a waste of money because your system is already lower than its maximum capacity, and then also you're literally just throwing refrigerant away. Liquid charging. Liquid charging is always faster than vapor charging because liquid is far denser than vapor, and taking liquid out of the refrigerant cylinder does not affect the cylinder pressure. On smaller systems, liquid charging is usually done with the compressor off. Prior to charging, the system must be leak tested and evacuated. On larger systems, a king valve located between the condenser and the metering device offers a convenient means of charging the system on the high side with the compressor running. Low pressure chillers are charged through the evaporator charging valve. Liquid should not be charged into evacuated chillers or units with water-cooled condensers. Let me just go back really quick. This is your king valve. Oh, didn't mean to move it. This is your king valve right here. You've seen smaller versions of that in class on the smaller training units, the little refrigeration units that we'll get a chance to work on when everybody comes back. But yeah, so that's what a king valve looks like. Vapor charging, small appliances, total system charge is 1 pound. So a small appliance is considered, or an appliance containing 5 pounds or less refrigerant is considered a small appliance. Evacuate the system, introduce vapor into the static equalized pressure, or equal to factory specs. So on smaller systems, you want to vapor charge it and you want to do it to factory specifications, meaning if it calls for 1 pound, put 1 pound in. On larger systems or on split systems, often you would end up needing more than what was specified on the data tag, but that's only if the line set is longer than 15 feet. The units all come pre-charged up to 15 feet of line set. So if your evap coil is more than 15 feet away from your condenser coil, well then now you got to add refrigerant. And the best way to do that is to check the subcooling and just add a little bit gradually till you get to your desired or your target subcooling. Vapor charging, heating the refrigerant cylinder. This raises the refrigerant temperature and pressure and allows the charging process to continue. Vapor charging with a unit operating, most vapor charging is done with the compressor operating because the compressor will actually aid in you charging that system because you're charging through the low side, which is the suction side, which is pulling into the compressor. So the compressor will literally suck the refrigerant out of the cylinder for you and assist in charging that unit up. The pressure difference between the tank pressure and system evaporator pressure will be greater as vapor is introduced into the low side. It should say as vapor right there. But yeah, so one of the questions I get was, can you charge through the high side when the system is running? Well, no, because, in some cases, but it depends on the unit. But the high side pressure is going to be higher than the pressure in the cylinder. So it's not gonna go in. If anything, it's gonna want to shoot pressure back into the tank. So you're gonna want to do it on the low side, and you're gonna want to vapor charge on these small appliances. And again, the compressor is going to assist with that because it'll literally be sucking the refrigerant out of the cylinder. Charging zeotropic refrigerants. Refrigerants that fractionate, such as 410A, must be charged as liquid. This prevents the separation of the refrigerant. So zeotropic blends, it's blended refrigerant, and they have different rates of evaporation. And so in vapor form, it's when vapor form, it's like a different refrigerant, but in liquid, it's easier to work with, because it doesn't separate. Weighing a liquid charge into an evacuated system is the same with zeotropes as with regular refrigerant, non-blended refrigerant. In both cases, refrigerant leaves the cylinder as a liquid. Factors affecting system pressures. The major difficulty in checking system refrigerant charge by measuring any single aspect of its performance is that there are so many variables that can affect system performance. The high side pressure on air-cooled systems is affected by outdoor ambient temperatures as well as airflow across a condenser. The high side pressure on water-cooled systems are largely determined by condenser inlet water temperature and the water flow. Condenser water flow has a large impact on high side pressure in water-cooled units. Return air wet bulb temperature has a big effect on evaporator temperature and pressure in air conditioning systems. The airflow across the evaporator in an air conditioning system is also critical. So again, if there's poor airflow across that evap coil, it will ice up in the cooling mode. It'll even cause problems in the heating mode if there's low airflow. It'll keep tripping your high limit switch. And then the airflow across your condenser coil, also extremely important, because at the condenser, that's where we want to reject heat. We want to use the cooler outside air as a means to transfer the heat energy from the refrigerant into the outside air. And then that fan blows that up. When the condenser fan is turning, it's pulling that cooler outside air across it and then blowing the warmer air out of the top. And it can't do so if the condenser coils are clogged up with dirt, or if I've seen people have like plywood and junk in the backyard leaned up against the side of the unit, or even have shrubbery around the unit that's too close and not allowing good enough airflow. So how are you going to remove heat if you can't pull in enough air? So the head pressure is going to shoot through the roof, and your system's going to cut off on high head pressure. And you're going to be chasing your tail trying to figure out what's going on. That condenser needs airflow. It needs plenty of airflow. It needs to be clean. So the condenser coil and the evap coil both need airflow. It's very critical. Again, the three mass fluid flows in an air conditioning system are your refrigerant flow, your airflow across your condenser coil, and your airflow across your evap coil. Those are your three mass fluid flows. All three need to be correct, or you're going to have problems. You're going to lose efficiency. You might even break something. So definitely keep that in mind. You have three mass fluid flows, and your refrigerant is one. You want to make sure that you have enough refrigerant in the system, and you want to make sure that it's actually circulated, meaning that the compressor is pumping correctly. You don't have a restriction at your THV or your metering device. You don't have a restriction at your liquid line, your liquid line dryer. And then with your airflow across your evap coil, keep a clean filter, keep a clean coil, and make sure that your fan, your blower motor is performing the way it's supposed to be. And then the same goes for the condenser coil. Make sure you keep a clean condenser coil, unobstructed condenser coil, make sure that fan is working the way it's supposed to be, and your three mass fluid flows should be fine. Standard industry design and operation. So there are system operating characteristics that become industry standards through common use. The primary rating condition for AHRI listed unitary air conditioning equipment is 95 degrees Fahrenheit outside and 80 degrees Fahrenheit inside, and 67-degree wet bulb inside. So what that means is the system is designed to be able to perform under those conditions. We turn the AC on when we're hot so we can cool down. So 80 degrees inside is when we're uncomfortable. We want to bring the temperature down. So the system is designed to operate when it's 80 degrees inside and it's 95 degrees outside. I would call that a pretty warm day. I would probably turn my AC on under those conditions. With that being the case, the condenser should be the refrigerant in the condenser should be at least 30 degrees warmer than the outdoor ambient temperature, which is 95, in order for the heat transfer to take place. Because remember, second law of thermodynamics is heat energy travels from hot to cold. So we need the condenser temperature to be hotter than the outdoor temperature, so that the heat transfer process can take place and we can lose all the heat that's in the refrigerant to the outside air. And the same thing's happening on the flip side in the evap coil. We need that evap coil to be at a cool 40 degrees because we got 80-degree air coming in. And so when that 80-degree air comes in through the return and we got that 40-degree refrigerant in that coil, that heat transfer is going to take place again. And all the heat energy in that air is going to be absorbed into the evap coil, and the air is going to come out of the other side, nice, cool, conditioned air. So that's how that whole thing works. So those are the design conditions: 80 degrees inside, 95 degrees outside. And so with the condenser needing to be about 30 degrees warmer than the outdoor ambient air, the condensers typically operate at 125 degrees. Water-cooled condensers typically operate at lower head pressure than air-cooled condensers. The common design for air conditioning evaporators has been 40 degrees Fahrenheit, when the air flowing across the evaporator is 80 degrees Fahrenheit and 67 degrees wet bulb. New equipment designed for higher efficiency typically operates at slightly higher evaporator temperatures. Standard airflow across an air conditioning coil is 400 CFMs per ton. So that means on a 2-ton system, you need to be moving at least 800 CFMs of air. This is a commonly applied standard. The temperature drop across an air conditioning evaporator is typically around 15 degrees at the ARI design of 80 degrees Fahrenheit dry bulb, 67 degrees Fahrenheit wet bulb. Expansion valve superheat settings vary with the different design and temperature range of the system. The system superheat of a fixed restriction system or fixed bore metering device varies widely with the system operating conditions. The subcooling on most correctly operating refrigeration systems is between 5 and 15 degrees Fahrenheit. All systems should have some subcooling. So between 8 and 15, or is it 8 and 12? You'll hear different rules of thumb out there. Between 8 and 12 or 8 and 15 is the typical superheat, but you can always just go by the charging chart to get the actual target superheat. And then when it comes to the subcooling, your default subcooling will be 10 degrees Fahrenheit. That's a rule of thumb you can keep with you in the field. If there's a charging chart available, definitely use it. We went over it before in class, so we'll go over it again however many times we need to, so everybody can get it, or at least get the ones that we have here, because they do change from one manufacturer to another. But there's usually a charging chart that'll tell you what the target subcooling will be for that unit under those current conditions. It's going to require you to take a few temperature measurements of the ambient air and things like that. But if there is no data tag, or if there's no target subcooling on the data tag or a charging chart, then you can default to 10 on your subcooling, and that'll get you pretty much where you want to be on your subcooling. Manufacturing charging chart. So here's a charging chart. So red line, red line, overcharge example, blue line, correct charge example, green line, undercharge example. So the blue line is correct. So let's go ahead and Open that up a little bit bigger. All right, so this is a 410 charging chart. Liquid pressure. So if your liquid pressure is about, what is this? This is 250, that is 300. So that'll be 55, 60, 65, 70, 71. So let's call this about 275. Your liquid pressure is about 275 and your suction pressure is about 130, then your charge, your let's go over here, and your outdoor ambient is about 85. So if your outdoor ambient is 85, your liquid pressure is about 375 and your suction pressure is about 130, then you're looking good. That's where you want to be. Oh, no, I'm sorry. I'm looking at the wrong one. My bad. You're not looking good. Green, undercharge. So blue is correct. So if you're at about at 85 degrees, 140 on the low side and around 300 on the high side is good. That is an accurate charge on this system according to this charging chart. Checking system superheat. System must operate for at least 10 minutes. After any charge adjustment, repeat the test procedure, ensures charge is within the proper range. So basically, if you check the superheat and it's incorrect, then you need to make it, well, before you check it, when you turn the system on, you want to give it at least 10 minutes to run. Some say 15, some say 20, but 10 is acceptable. Usually when I arrive at a service call, I consult with the customer for a moment. And then at some point during that consultation, I'll turn the system on from the thermostat. And then I'll kind of let it warm up, start doing what it does, continue my conversation, till we're done. And then I'll start doing my little checks. But pulling out my gauges is usually the last thing I do. Anyways, point of me bringing up the whole procedure is 10 minutes will have passed by the time I get to the point that I even need to put my gauges on the system. And if not, I'll continue to wait. If I feel like I need to, if this is a refrigerant issue that I kind of figured out right away, then I'll go ahead and hook my gauges up. And I'll just watch it, and I'll give it at least till that 10-minute mark before I start making my, judgment calls, because the temperatures and pressures, they'll bounce around a little bit. So you got to give it about 10 minutes to stabilize. And then if you make an adjustment, you want to give it another 10 minutes to stabilize before you decide, okay, that one didn't do it. I need to make further adjustments. So one of the best things you can be in our trade is patient. Just be patient. A lot of times problems will hide from you or take their sweet time to show up, or the solutions might take a while to kick in. So you just got to give yourself time, let the system do its thing, and let your pressures and temperatures stabilize. Charging for proper subcooling. Thermostatic expansion valves. So when it's a system with a thermostatic expansion valve, that's when you want to charge by subcooling. Regulates the refrigerant flow over a wide range of load and charge conditions. Thermostatic expansion valves try to maintain a constant superheat. This means the superheat method is not the best method for testing the charge in an expansion valve system. So TXVs or TEVs, they modulate. So depending on the load on the evaporator, basically the more heat going across that evaporator, the quicker it's going to boil off the refrigerant, the more the TXV is going to open up to let more liquid come in so that it's not boiling off too fast. The lower the load or the lower temperature going across that coil, the slower that refrigerant will boil, and then the TXV is going to close and let less liquid refrigerant in so that we don't flood the evaporator and allow it to boil off before it goes back to the compressor. So they modulate, and the fact that they modulate make it kind of a bad place to check, for your when it comes to charging your system. So on units that use the TXV, we go by the subcooling. But on fixed orifice or fixed bore systems or restricted orifice systems, whatever they call them, anything that's not a TXV, anything that doesn't modulate, a piston, especially a piston or a capillary tube. If you have one of those, then you go by your superheat. So checking system subcooling. System must operate for at least 10 minutes, same when you're checking the evaporator. After any charge adjustment, repeat the test procedure, ensures charge is within the proper range. So on subcooling and superheat, on both of those, you want to still kind of approach it in a similar way, which is give it time, give your pressures and temperatures time to stabilize before you make a call whether or not you're off or if you're correct. So you want to give yourself some time, and then when you, again, like for example with the subcooling, if you're at 10 degrees Fahrenheit, then you're probably okay. And there's a little bit of an allowance, if you could be, I would go maybe two degrees plus or minus. So if you want 10, anything between 8 and 12 will be acceptable. And the same on the superheat. You give yourself a little bit of an allowance, because it's not always going to be exact. It's not going to be the exact number every single time, especially with conditions changing constantly. So, but to clarify again on what superheat and subcool is. So superheat is adding the heat energy added to a vapor above its saturation point. So basically the vapor has already boiled into a vapor from a liquid already. And it's going to continue to absorb more heat energy, and to ensure for a fact, without a shadow of a doubt, that there's no liquid going back to your compressor. Similar thing on the opposite end of the system with the subcooling. We are removing heat from a liquid that's already had heat removed from it to the point of condensing it back to a liquid already. So we're removing heat from a liquid below its saturation temperature. So it's already condensed back to a liquid, and we're removing more heat just to be 100% sure that we're only sending liquid to the TXV, because we want all liquid going to the TXV. So that's the whole point of the superheat and subcool. So if your charge is correct, then you would have the way the system is designed. If your charge is correct, you will have 100% liquid going to the TXV, or you'll have 100% vapor going back to the compressor, because of the way it was engineered. So if you don't have the right amount, if you have too much liquid and now you got liquid coming back to your compressor, that's an indication, like, okay, there must be too much liquid, too much refrigerant in this thing, because the way it's designed, it should have fallen off by now. Or the opposite, the way the system is designed, it should be, it shouldn't be boiling off at that rate, so you don't have enough refrigerant. So that's the point of superheat and subcool, is telling you yes or no, I have enough refrigerant in this system. Liquid ambient approach charging method. So temperature differences. The liquid line is always a little warmer than the outdoor ambient temperature. The approach charging method examines the temperature difference between the liquid line and the outdoor ambient temperature. Calculating the approach. Measure the liquid line temperature and subtract the outdoor ambient temperature. Use the same thermometer to take both readings to validate accuracy. A few degrees difference can give a different diagnosis. And I've had, one thermocouple read one temperature and another one read differently. So when doing the approach method, definitely want to check or use the same thermometer. So on water-cooled systems, first check water temperature and then water flow. So water temperature, if it's too cold, it will give you low pressure readings. It's going to give you an undercharge, symptoms of undercharge. And then with your water flow, if you have too little water flow, you're going to have higher than normal pressures. It's going to give you overcharge characteristics. Oil charging. Cleaning a system with multiple compressor failures. Check the compressor oil, change the compressor oil. One of the fastest ways to clean a system that has experienced multiple compressor failures is to check and change the compressor oil. Oil changing, hermetic compressors. It is not practical to remove oil from hermetic compressors. Hermetic compressors do not have crankcase ports. So this here is why I have not done a whole lot of oil changes, because on the equipment that I work on the most, which is residential and light commercial, they're all hermetic compressors. Those semi-hermetic compressors with those heads on it that you can, remove and actually get in there and work on them. Those are the kind that you actually would do repairs on or do your oil changes on. Semi-hermetic or open compressors, adding or removing oil is more reasonable with these compressors. So that you can change the oil, absolutely change the oil on both types of systems. And I have changed the oil on a hermetic compressor because it became contaminated, but it's just not something that is often done. Small semi-hermetic compressors have a crankcase plug above the normal crankcase oil level that may be used for removing or adding oil. That doesn't exist on hermetic compressors, but it does on these semi-hermetics. Oil charging, using vacuum to add oil. In the evacuation method, the compressor creates a slight vacuum that is used to suck oil in, purge the air from the oil line by blowing a small amount of refrigerant vapor through it into the oil. So in summary, a system that has been evacuated is normally charged with liquid into the high side of the system with the system off. The amount of refrigerant added is measured by an electronic scale. The amount and type of refrigerant used in the system can be found by looking at the data plate on the unit. Common forms of charging charts provided by manufacturers include charts that correlate operating conditions to system pressure, superheat or subcool. Superheat charts are used with fixed restriction systems, while subcooling charts are used with thermostatic expansion valve systems. So I'm gonna go ahead and stop that. Hopefully that was helpful. That was unit 29 or chapter 29 for mod 135. The rest of the info will be in your book, and the review questions are on FlexiQuiz. So handle your business, and I will talk to y'all later.